Okay, so in this video, we will be focusing on the last part of chapter 7, which is heat of the reaction. So, almost every chemical reaction involves loss or gain of energy. Every reaction basically would involve either some energy being gained during the reaction or lost, which means either heat is being exiting the reaction or it is being absorbed during the reaction. This energy most of the times is in heat energy. Therefore, it is also referred to as the heat of the reaction. So, for every reaction, there is a change in the heat that happens, which could be the amount of heat that is absorbed or it is released during a reaction at a constant pressure. Whenever a reaction is happening at constant pressure, there is always a change in the amount of heat that is absorbed or released during a reaction, and that is referred to as heat of the reaction. This heat is usually involved in a reaction whenever reactants interact with each other. When they interact, some bonds need to break apart, some new bonds need to form, and therefore products are formed. So this whole process of breaking bonds and forming new bonds would require some change in the energy in the process, and that's where this heat of the reaction comes in. Now, when we talk about in chemistry, this heat of the reaction is defined as enthalpy for a reaction. So enthalpy is essentially the difference in the energy of products and the energy of reactants. So we take the energy of the products and we take energy of reactants, we calculate difference between those, and that is how much energy difference is involved during a reaction. And that is referred to as change in enthalpy, and it is given by this symbol, which is called delta H. Delta here basically is this triangle. This is usually referred to as delta, and H here stands for enthalpy. So delta means change in enthalpy of products and reactants, and this is usually given by this particular formula where delta H is H of the products minus H of reactants. So enthalpy of the products minus enthalpy of reactants. It's always product minus reactant. So whatever is the energy of product minus energy of reactant, that would be the heat energy that is involved in a reaction. And the SI unit, for energy we have seen before is joules, or it can be kilojoules. Okay, now this delta H can be a positive value or a negative value, and that depends on if the reaction is exothermic or endothermic. We have previously in a previous chapter talked about what is an exothermic reaction. An exothermic, exo means exit, thermal means heat. An exothermic reaction is a reaction where heat is released, energy is released. So in this case, when does this happen? Whenever reactants have higher energy. So you can see in this energy diagram, this is on the x-axis we have progress of the reaction, and on y-axis we have energy that is involved in a reaction. So reactants here have high energy and products have low energy. When the the reaction is going from reactant to product, so whenever it goes from reactants to products, since the total amount of energy of product is less, the excess energy that these reactants have will be released, and this released energy makes this reaction an exothermic reaction. So here always the energy of reactants is more than products, or energy of products is less than reactants. Here heat is regarded as a product because in this case what is essentially happening is that reactants have more energy, they are converted into products, and they have some extra energy which is also released in form of heat during the reaction. So as it is released, it's exiting the reaction, it is one of the products. So heat is regarded as one of the products. Whenever heat is released during a reaction, then the value of delta H will always have a negative sign in front of it, which means delta H for an exothermic reaction will always be negative. Okay, this is something you should memorize. Whenever you see that delta H for a reaction is a negative value, that means this is an exothermic reaction. For instance, in a reaction of hydrogen with chlorine, it produces HCl. This reaction is a highly exothermic reaction. It produces 185 kilojoules of energy. So delta H here would be H of products minus H of reactants, and that would give you minus 185 kilojoules, which essentially means this is happening because reactants have higher energy. So when you have a smaller number minus a bigger number, which is reactant energy, it would give you a negative value at the end. Okay, so what you need to memorize here, what is exothermic reaction, and that delta H for an exothermic reaction is always a negative value. Next type of reaction is an endothermic reaction. My apologies, this should be endo. Let me cross this out. This is not exothermic, this is endothermic reaction. Okay, so this is an endothermic reaction. You can see right here, this is an endothermic reaction. Endo means getting in, thermal means heat. So an endothermic reaction is a reaction where heat is absorbed during the reaction. Here, if you look at the energy diagrams, reactants have low energy, products are high in energy. So when reactants are getting converted to products, they need to absorb, in order to match their energy level, they need to absorb some energy from outside, and this absorbed energy difference is called delta H. So this is the difference in energy of product and reactant. So this difference is called as delta H. So you can look at the energy diagram and you can predict or tell what is the delta H here. Again, delta H here will also be product minus reactant. But in this case, since products have more energy, your final answer will always have a positive value. So in case of an endothermic reaction, delta H is always a positive term. And since heat is being added in this reaction, if I were to write this reaction, reactants are getting converted into products, and since heat is being absorbed in this reaction, heat is one of the reactants as well. Okay, reactants are absorbing this heat and then converting into products. This is an example of an endothermic reaction. Now, how can we why are these values of delta H important for us? The value of delta H is, for instance, the value of delta H refers to the heat change for each substance in the balanced equation. So for example, if we are looking at this particular reaction, 2 moles of water here are converting into 2 moles of hydrogen and 1 mole of oxygen. For this reaction, delta H is 572 kilojoules. It's a positive value, which means heat here is being absorbed in the reaction. So this is an example of an endothermic reaction. So we can write this reaction as 2 water molecules plus 572 kilojoules of energy will convert this water into hydrogen gas and oxygen gas. Therefore, here 572 kilojoules is one of the reactants. So now how we did the stoichiometry, this same rule applies here. So we can make this into a conversion factor. For every 2 moles of water, that is, for every 2 moles of water that is broken into its product, will require 572 kilojoules of energy. Okay, so this is our conversion factor if we are trying to go from moles of water to kilojoules of energy that is needed. Same thing we can do between hydrogen and energy. So for every 2 moles of hydrogen gas produced, 572 kilojoules of energy is used. Similarly, we can make a relationship between oxygen and 572, which is for every 1 mole of oxygen molecule that is being produced, 572 kilojoules of energy is absorbed. Okay, just be very careful with the sign of delta H. Delta H, if it has a positive sign, it is the heat that is absorbed. If it has a negative sign, for all your conversion factors, you would include that negative sign. Okay, you can expect here something like this. How much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? So question, what's given to us in the question is that we have 50 grams of ammonia is being produced. The question is asking how much of heat in kilojoules is released in this process. So we need to go from grams of ammonia to heat energy released in the process. Do we have a direct relationship here? No. But we know that delta H for this reaction is minus 92.2 kilojoules. So we can make a relationship between moles of ammonia and kilojoules of heat. So from based of this reaction, we can say that for every 2 moles of ammonia that is produced would release 92.2 kilojoules of heat. So that negative sign is how much of heat is released. So if we are saying that heat is released, we really don't need the negative sign. If we are putting a negative sign, that means this heat is being released. Okay, so I know a relationship between moles and kilojoules, but I don't know a relationship between grams and kilojoules. So that means I'll have to add a step in between where I can go from grams to moles, where I can go from grams to moles of ammonia, and then from moles of ammonia I can go to kilojoules of ammonia. What is the conversion factor to go between grams and moles? Again, it is molar mass. Since our molecule of interest here is NH3, we want to find what is the molar mass of NH3. That consists of one atom of one atom of nitrogen. Nitrogen is 14.00 gram. Plus we have 3 atoms of hydrogen, so it is 3 times 1.01 grams of hydrogen. That would give you a total weight of 17.01 grams of NH3, which is ammonia. So our conversion factor here is that 1 mole of ammonia is 17.01 grams of ammonia. That is our first conversion factor. And the next conversion factor between moles and heat is right here. 2 moles of ammonia is 92.2 kilojoules of heat. Like I said, if you will put a negative sign, that means it's released, or if you don't put a negative sign, you just have to mention that this heat is released during the reaction. Okay, so we start with, again, what's given to us, 50.0 grams of ammonia. Once you have solution map, you begin with your first step in your solution map. Now I want to cancel the grams of ammonia, so I'll divide by grams of ammonia based on this conversion factor and multiply by the other side, which is moles of ammonia. How many moles? 1. How many grams? 17.01 grams of ammonia. Grams and grams got cancelled. My answer is in moles of ammonia, which is right here. So I'm at this step now. Now I can go from moles to heat, and I need to use this conversion factor for that. Now to cancel moles, I'll divide by moles of ammonia and multiply by kilojoules of heat released. Okay, how many moles of ammonia? 2 moles. How many heat? How much heat? 92.2 kilojoules. Now moles and moles got cancelled. Our final answer is in kilojoules of heat. If you plug this into your calculator, that would give you essentially 50.0 times 92.2 divided by 17.01 divided by 2, which is 135.5085 kilojoules of heat. How many sig figs do we want in our final answer? We have 1, 2, 3 sig figs. So 1, 2, 3 sig figs, which means our final answer would be 136 kilojoules of heat is released. Sometimes you might, instead of seeing the word released, you might see it written as minus 136 kilojoules as one of the options if it's a multiple choice question. And in that case, you want to choose the option with the negative sign, because in this case heat is being released, so negative sign signifies the release of